Hello and welcome to our Siemens webinar. My name is Johannes Bruß and I'm the responsible product manager for Cyprotec Arc Protection Solutions. It's a great pleasure for me to be here and I would like to thank you very much for your participation. In this video I want to provide you with an overview of arc flashes, how they occur and why they are so dangerous. Electric arcs are among the most dreaded fault scenarios in power supply engineering. While it's fascinating to watch, an arc flash can be extremely dangerous. So what is an arc? The technical definition of an arc flash is a flashover through the air from one exposed live conductor to another conductor or to the ground. Hot and ionized gas, a so-called plasma, is formed between both electrodes. This plasma leads to a short circuit that maintains the high temperature of the arc. So in a simple way, it's an electrical explosion with extreme heat, light and sound. Now, what does lead to an arc flash? Arc flashes can be caused by a multitude of factors, like for instance design and electrical system failures, as well as dimension of the equipment, or design and manufacturing mistakes. Another factor is the normal wear and tear and the aging of insulation materials. The reason can also be environmental influences like humidity and pollution, which might lead to the corrosion of electrical contacts. Also, rodent entry can be a root cause. However, the most common reasons are human errors and maintenance issues, like operational mistakes, wrong installations or missing maintenance. So how does the spectrum of an arc flash look like? The typical spectrum lies between 300 nanometers and 800 nanometers, so mainly in the range of the visible light, with a maximum around 500 nanometers. The spectrum contains peaks which are strongly dependent on the material. In case of copper, we can see strong peaks especially at 550 nanometers and 521 nanometers. Other materials will lead to peaks at a different wavelength. When we look at the intensity, it's interesting to see a pulsation of the light with twice the power grid frequency. Reason is that the arc intensity drops with each zero crossing. We learned what an arc flash is and how an arc flash can be caused. Now we want to talk about the dangers and risks that are associated with an arc flash. An arc flash is not as seldom as you might think. According to a study from the Fire Protection Research Foundation, an estimated 5 to 10 arc flashes occur in electrical equipment in the United States each day. This results in roughly 2,700 cases per year, only in the US. And the consequences of an arc flash are severe, not only to the equipment. The intensive flash can damage the eyes and lead to a shock reaction. The extreme sound can lead to hearing damage. The enormous pressure can lead to flying parts of the switchgear. And finally, the extreme heat of the plasma that can lead to severe burning and the contamination of toxic gases. So besides the destruction of the material that can lead to outages, it's a serious hazard to operating personnel as well. We talked about the dangers of an arc flash, but how does an arc flash look like in reality? Let's see this video. Impressive, right? You wouldn't want to be standing next to that. So let's see how an arc flash causes damage. The degree of damage caused by arcing depends principally on the duration of the arc. In the beginning, we see a strong pressure peak after around about 10 milliseconds. The pressure is then decreasing, but after 100 milliseconds the thermal phase starts. The consequence is that you cannot avoid the pressure peak with the conventional approach to trip the circuit breaker, as the circuit breaker will need round about 50 milliseconds to open. However, you can avoid the thermal phase that leads to severe damage. So what does severe damage mean? An arc flash leads to extremely high temperatures that can reach around 10,000 degrees Celsius. Just for comparison, the temperature on the surface of the Sun is only 6,000 degrees Celsius. This extremely high temperature causes melting, vaporizing and destruction of the switchgear materials. The thermal damage starts after 100 milliseconds with the destruction of the cable sealing ends. After 150 milliseconds, the copper components start to melt, followed by steel 50 milliseconds later. This picture here on the right side shows the destruction of a cable connection compartment after an internal arc flash test. So how does an arc protection solution minimize the damage? In general, over current protection applications, the selectivity is given by time grading. In our example, we see a feeder with 4 sections. Each section has a circuit breaker and a protection relay. To make sure that you do not trip everything in case of fault, the overcurrent functions of the relays have a time grading. So if a fault occurs at the end, the relay can trip immediately. However, if the fault occurs at the beginning of the feeder, the time delay can be significantly longer, as in our example here, where the time grading is 300 milliseconds between the relays. Considering that the arc fault occurs at the beginning of the feeder, the relay that we see here on the left side would detect the fault and pick up. However, the relay would need to wait 900 milliseconds until it could finally trip the circuit breaker. Bearing in mind that the thermal damage starts already 100 milliseconds after the arc fault inception, you can imagine the extreme destruction after such a long arc fault duration. The big benefit of an arc protection solution is now that the relay on the left side is able to detect optically that is not a normal overcurrent fault, but a real arc flash. Instead of waiting for 900 milliseconds to trip, the relay can now immediately trip the circuit breaker. This minimizes the incident energy and the thermal damage significantly. So how to install optical arc sensors? In the slide, you can see a cross-section of an air-insulated NX-Air switchgear. This switchgear consists of 3 compartments: the busbar, breaker and cable connection compartment. As arcs can principally occur in all 3 compartments, it's necessary to install 1 sensor per compartment. This diagram shows the usage of 3 optical point sensors. In case of point sensors, the sensor head mounted in the compartment is optically sensitive. Alternatively, it's also possible to use a line sensor instead of point sensors. These line sensors are actually long fibers that can detect light along the whole surface. This brings a huge benefit, especially if you want to protect the busbar, as you don't need several point sensors, but you can place 1 line sensor along the whole busbar. One thing is very important. You want to detect an arc, but you do not want to trip in case of normal ambient light. So to avoid any overfunction due to ambient light, it's common practice to combine the light signal with an overcurrent pickup. We heard a lot about arc flashes and arc protection. So why is protection against arc flashes essential for you? Arc protection allows extremely fast tripping time, bypassing the time grading delays required by standard overcurrent protection relays. This limits your damage, especially the thermal destruction, which finally increases your system availability. And most important, it increases personal safety significantly. I hope you enjoyed this webinar. If you are further interested in arc protection, I'd like to invite you also to watch the upcoming webinars of our arc protection series. Stay safe, take care, and goodbye.